Saxon Advanced Mathematics, Lesson 59, Logarithms. We are definitely pushing into some of the hardest log problems that we'll be doing, thus the advanced. Let me just review a couple little things for you before we dive into the actual problems. Here's one kind of expression that we've learned how to simplify. We have logs with matching bases on each side. So what we're saying is that the exponent that you put on 4 to get x plus 2 is the same exponent that you put on 4 to get 5. So if those two things are the same, then we know that if the bases are the same and the number is the same, then the exponent must be the same. So we can simply say x plus 2 equals 5. And then we can solve that x must equal 3. I did that in my head. And then we always have to test to make sure the argument is positive. A second, I'll elaborate. The exponent is this part, or the argument is this part. It's the number, if you will. That has to be positive in a logarithm. So when we get our answer here, we just plug it back in to make sure that's a positive number. X could be negative, but the argument has to be positive. And it is, so we're good. And that's our answer. Okay? So that's where, when we have matching logs on each side, we can lift that off and solve it. However, there's a different kind of problem that looks like this. It's an equation. This does not have the log on this side, right? There's the log over here with the base, but this is just the plain number, and we have to try and solve it for that. So what we're saying is that the exponent that we put on 4, 2 is the exponent we put on 4 to get x plus 5. So what we have to do with these, instead of lifting off, we have to switch. Just a second, let me just write this. This is a lift-off strategy. And this is a switch to exponents. And I'm not sure if that makes sense. But what we do for this one is we say that x plus 5 equals, right? That's the number. This is the base, and that's the exponent. So we switch it to an exponential equation. Okay? Think back to the original form of what an exponent is. That's the base, that's the exponent, and that's the number that you get. So that's what we did here. We said, okay, this is the number that you get when you put that base with that exponent. And that's what I wrote here. And then we know that x plus 5 then must equal 16, and then we get x equals 11. We check again to make sure it's okay, and we're good. Okay? So these are two reminders of the different strategies that we use depending on what our logarithmic equations look like. Now let's actually try an example, right? That was just the warm-up. I'm sorry. Solve. Oh, this is equals, sorry. All right. So when I look at this, what I notice is we have the first kind, right? We don't have any just plain number there. So I'm going to be able to lift the I'm going to be able to lift off the arguments and solve them separately. But first I have to clean them up, because in order to do that, I have to have just log and log on each side. This one I need to use the power rule, and this one I need to use the quotient rule, don't I? Because I've got subtraction there, so I know I can divide. So I'm going to rewrite this as log 10x to the third power, and I'm going to rewrite this as log 10 to the 16 over 2 power. And then I can simplify this to just 8. But now, because I have log 10, now I can say x to the third equals 8, and then that gets me quickly to x equals 2. Check to make sure. Yes, that's a positive argument. That's the only variable in the argument. I'm good. That's the right answer. These were the right answers too. All right, so that was an example of the first type. Now guess what? We're going to have one of those. How did you know? You're so smart, students. Okay, example 59.2. Solve. Second, I don't have enough light on my book. I should change my timers. I have timers on the light in this room, and so at a certain point the lights go out, some of them, and then I can't read my book as well. Okay, so I've got two log expressions being added on the left, and then I have a plain number on the right. So what that tells me is I need to smush them. I need to smush these arguments using this will be the product rule because I'm adding, right? And then I'll have to use I'll have to convert this to an exponential equation. So let's put these two together. We're adding, so that means we multiply. Log 7, that's a 7, times the quantity x plus 1 times the quantity x minus 5 equals 1. That stays the same. Okay, now what we're saying is 1 is the exponent that you put on 7 to get that as your result. So I can write that. I'm going to write x plus 1 times x minus 5 equals 7 to the first power. Interesting, right? Now we'll multiply this out. I can do it in my head at this point. X squared, I know this will be what? Minus 4x minus 5. And then this 7 I'm going to swim over. Right? It's a positive 7 here, so it'll be a negative 7 when I change sides. Now I've got all the numbers on one side, and hopefully I can resolve this without too much drama. Whoops, x squared minus 4x minus 12 equals 0. Oh, I think we can do this by inspection, right? We can do x minus 6 and x plus 2 equals 0. That means x equals 6 and minus 2, right? The solutions are the opposite of those. Now let's check and see which of these two values work. So let's try 6 first. Does 6 work here? 6 plus 1 is 7. Yeah, we're good. 6 minus 5 is still positive 1, so we're good. So this one checks out. Minus 2 plus 1 is minus 1. So right there we have a failure, and then it fails again. All it has to do is fail once, and it's bad. So I'm going to cross that one out, and this is what I would want to see on a test or a review problem. I want to see that that was considered and eliminated as a possible answer. All right. Okay, so that now we've seen one of each style of problem. Let's see what John throws us in this one. Solve. It's log. Excuse me, I need my light better. 3x. Okay. So we look at this one and we see, okay, we've got some log business we can clean up over here, but this side is a plain number. So this is going to be the type 2 where we're going to convert it to an exponential equation. So the first thing we'll do is clean up on this. I'm going to take this and use the power rule first. Log 3x squared. And then I can, well, I'll just write it out. I'll do it in 2 steps. I don't want to confuse you. Now I see I'm subtracting. That tells me I can use the quotient rule and I can divide the arguments. Log 3, and it will be x squared over x minus 2 equals 2. All right. So what that tells me is that the exponent 2 is what we put on the base of 3 in order to get this as the result. So I can write x squared over x minus 2 equals 3 squared. Looks crazy, right? All right, let's, this we know is 9. I'll fix that. Let's cross multiply. And I'm going to work here because I don't want to flip the page on us. Okay, so I will have 9 times this, right? Because I'm cross multiplying here. So 9x minus 18 equals, and then this is just plain because it doesn't have anything down there, so it's over 1, equals x squared. Okay, now I can swim everybody over and see if we can solve x squared plus 18, plus 9, no, sorry, let me start over. X squared, when he comes over, he's going to be minus 9x. When he comes over, he's going to be plus 18. 0. Okay. And let's see. This one is solvable by inspection too. I'll give you a minute to think about it. See if you can find the pairs. X minus 6, x minus 3. Right? They multiply to positive 18, they add to negative 9. Yay. That means x equals 6 and 3. Now we have to do our checks. This argument is just a plain x. They're both positive. That's fine. X minus 2. Yeah, we're good on both of those, right? We'll still get a positive number. All right, so we can include both of these as our solution. And we're good. All right, so those are advanced log problems of one type. Well, technically there are 2 types, right? And we talked about here. Some you can just lift off, others you have to simplify and then convert to exponential problems. But now there's a third kind. Ay, 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 John, always with another little something, right? These are so easy that they're almost hard. Let me show you how it looks. Here's what this says. 42 raised to the power that 42 must be raised to in order to get 5. 42 raised to the power, because log always means power or exponent. 42 raised to the power or exponent that 42 must be raised to get 5. So the answer is 5. I'm going to write that out again. Please copy this, because it's so much easier if you can say it to yourself. Okay. John says he's trying to explain this in the book, and he says some really whack random things about the color of the White House is white and the color of the Red House is red. Don't listen to that. That will make you crazy. That's a metaphor that I'd love to wrap my head around, but it's just confusing. Just realize that this is what he's saying. 42 raised to the power that 42 must be raised to get 5? The answer is 5. Okay, that is 59.4. Now we're going to take this same idea and wrinkle it just a little bit. Here we go. Okay, 9 raised to the power that 3 must be raised to get 5. That's confusing because this base doesn't match this base, and before they matched. But we see, oh, wait a minute, 9 can be rewritten as 3 squared, right? 9 is 3 squared, and then we multiply that times the rest of that nonsense. Okay, so we switched the 9 to a 3 squared, so now the bases match. But now we've got this creature. What do we do with that? Oh, we can jump it up on top of that 5, right? We can use the power rule. So now we say 3 log 3, 5 squared. And I'm just going to change that to a 25 right away. So now we're saying 3 raised to the power that 3 must be raised to get 25. And so guess what our answer is? 25. Weird, right? This one, the trick was to recognize that the base in this didn't match the base here, so we had to fix that. Let's try another one. How many are there? I think there's a couple more after this. Yeah, there's a total of 9, but there's not a lot of work to them. We're just learning the tricks. 59.6. Okay. 10 to the 4th power raised to the power that 10 must be raised to get square root of 3. That's a mess. We know we have to take this and put it on this, right? That's what we did here. The bases will match. We just have to get rid of this number. But we can't change the exponent on a root that's in a radical. But if we rewrite it as 3 to the 1/2, then we can, right? That will work. So that's what we're going to do. We're going to write it as 10 log 10, and then this will be 3 to the 4 over 2, which is equal to 3 squared, which is equal to 9. Does that make sense? And so the answer is then 10 raised to the power that 10 must be raised to get 9. And so the answer is 9. That's trippy, isn't it? This is just such a weird problem. This is the key. If you ever get confused on these, go back to this problem and read that over and know that we're trying to make the bases match here. The bases have to match. And then we have to get rid of, these are the rules we've found so far. Sometimes we have to use the power rule to get rid of the coefficient. So I'm going to write remove coefficient. Now let's see if we find any other tricks in these last few lessons. Let's try 59.7. There's not a lot of work to these. You just have to recognize the tricks. Okay. Okay, so 3 raised to the power that 3 must be raised to get 4 plus the power that 3 must be raised to get 5. aha, we recognize this as a situation that calls for the product rule, right? Because with the product rule, we can combine these by multiplying the arguments. So that becomes 3 log 3, and then 4 times 5 is 20. And so our final answer is 3 raised to the power that 3 must be raised to get 20. So there's our answer there. So what we see is that this isn't just removing the coefficient, but we might have to use our laws for logs, right? Which are the same as our rules for exponents. So that's what we did here, right? We used the power rule, but now we're using the product rule. So I made our rule broader to address all the scenarios. I hope this is making sense to you guys. I can see easily that you could just be sitting there going, what in the world is she talking about? That is my biggest regret with remote teaching, is that I can't see your faces. Okay, 57.8. Okay, this one's crazy. E is our base, and our number is E. This is our number. So they're saying, what exponent do we put on E to get E to the 14th? That's so easy, it's hard. What exponent do we put on E to get E to the 14th? 14. And this one again, if you just go back to the very beginning and remember how we did these, 5 is the base, 25 is the number. What's the exponent that we put on 5 to get 25? 2. It's so easy, it's hard. Okay? I am going to ask you about these. I can tell you right now I'm not going to give these to you as a review problem, but I am going to ask you about them when we video chat. Remind me if I forget to do so. But I want to see how your head is wrapping itself around these. Okay, that's the end of 59. Thank you. Goodbye. 60 is a little less head trippy. I mean, how could it get worse, right? Okay, bye.